So, the next step, once we know the eigenvalues, is to calculate the eigenvectors. So let's assume we know the n times n square matrix A, and we take one given eigenvalue lambda. From this, we can create the eigenvalue equation. And of course, the vector mu is our eigenvector. We've already seen when calculating the eigenvalues that this can be transformed to the difference of these two matrices, which is an n times n matrix, times vector is equal to 0 vector. This effectively has the following form. So this is nothing more than a linear equation system, and not only a linear equation system, but a homogeneous linear equation system, because our vector here at the right hand side is 0. So we have this homogeneous linear equation system. Let's just look at the first row of it, and then you will have an idea how the other rows look like. You see that you will have one lambda, which is a number which we know, we can put this in, and we have the a's which we know and can use, and as unknowns we have the coefficients of the mu. And we will have n different equations for our n unknowns. This is solvable, but the solution will not be unique. We will find an infinite number of solutions. And why that's the case, we will see in a moment. The solving of the eigenvectors gives you 1 degree of freedom. This is effectively the length of the eigenvector. The direction will be defined, but the length is free to choose. Why is that so? If we look at the eigenvalue equation again, then you see that I can put in any factor that I'd like, apart from 0, in between, and it will still hold true. So not only the vector mu is an eigenvector, but any vector in the same direction as mu is an eigenvector. I can use this factor because we are looking at linear maps. This is exactly a point of linearity that we are using here, which gives us this 1 degree of freedom in the length and orientation of the eigenvalue. What does this mean now? When the length is free to choose, have a look at the rotary matrix. In the rotary matrix, the eigenvector has the meaning of the rotation axis. The eigenvalue is 1, the vector doesn't change, this has to be the rotation axis. It doesn't matter how long your axis is, it's just important that the direction of the axis is given. And how do we deal with that? Which length do we choose? There's 2 choices. We can either choose the vector in a way that it's normalized, that its length is 1. That's a common choice. So you calculate any of your possible mu's, and then you divide this result by its absolute value, and of course you get an absolute value of the later vector as 1. The second point, which is often chosen, the coefficients of this mu, mu1, mu2, mu3, and so on, mu x, mu y, mu z, if we are in a 3-dimensional space, can be chosen so that they are easy numbers, that they are integers, that they are rational numbers. Most often then of course the absolute value is not 1. It's a choice, it's your taste that in the end will decide that, or whatever you're asked to deliver.